So in this video, I'm going to give you a proof by picture of Dirac's theorem about a sufficient condition for a graph to have a Hamilton cycle, meaning a cycle going through all the vertices. And the condition here from Dirac of this minimum degree, at least n/2, is a little bit simpler than this condition that's given in the book of a theorem by Aura, where you add up the degrees of non-adjacent vertices and stuff like that. And the reason I'm giving you Dirac's proof is that this condition is less confusing. The book only gives this as a corollary, but we're going to prove it straight away. So how do you prove Dirac's theorem? Well, it's not all that difficult. The idea here is typically if you look for a Hamilton cycle, you may look for something like the longest cycle in your graph. Of course, this works very often, this approach. For the proof of Dirac, it's kind of a little bit weird, but you don't actually look for the longest cycle to start, but instead you look for the longest path. So let's say we have a longest path in our graph. So there's vertices on here, and this is the longest path here. And what do we know about this longest path? Well, this longest path, if we look at the two end vertices, these big black dots here, they cannot have any neighbors outside of this path. Why not? Well, if I have a neighbor outside the path, I can make the path one longer. So this blue path would not be the longest path then. So all the neighbors of these two guys are on the path. So of course, this left guy, let's draw in all the red neighbors, all the edges of this left guy maybe. So, and color all these neighbors that he may have red here. So it has some neighbors on the path. And let's color all the neighbors of the right guy green. Of course, the first vertex is always the neighbor and so on, right? And maybe sometimes these guys are together and sometimes next to each other. So we know the minimum degree is at least n/2. So if I have this vertex u and this vertex v, if I look at the neighborhood of u plus the size of the neighborhood of v, this is at least n/2 plus n/2, which is n. So, well, if you look at this at first, well, what does this mean? Well, either every vertex of this whole graph is a neighbor of one of the two vertices, or there's a guy hit twice. So in this picture, this guy in the middle is hit twice. Does this help us? Well, like the picture looks like this, right? So this one's connected to this, and this one's connected to that. So hitting a guy twice doesn't really help us. But what would help us? Like, look at this picture. If I have something like this here, where the right vertex hits this and the left vertex hits the next vertex, I can look at this cycle all the way around like this, crossing over like so. And this gives us a cycle that goes through all the vertices of the path that I've drawn. Why would that help me? Well, if there's another vertex somewhere in the graph that's not on the path, it's connected here, and then I can take this path from this vertex to the cycle, and then walk around the cycle, pick up all the vertices, and have a longer cycle. So if I find a cycle like this, then I can either find a longer path, if there's a vertex left, or the cycle is already my Hamiltonian cycle. If there's no vertex off the path, then I already have a Hamiltonian cycle here. So this situation where a green vertex is followed by a red vertex leads to a proof of the theorem. Either a contradiction that I can make a longer path, or I have my Hamilton cycle. So now we have to think about, does this always happen? That a green vertex is somewhere immediately followed by a red vertex. Well, what does this mean? Green followed by red. It means that if I look at the set n plus of v is equal to the right neighbors of n of v. If I look at this set instead, and if this set and the neighbors of u, the red vertices, so the right neighbors of the greener vertices and the red vertices, if this set here, if this thing here is not empty, then we're done. So why is the set not empty? Well, of course, the set of the right neighbors has the same size as the set of the neighbors, the green vertices, right? So again, the same argument works. So we have n of these. The only way that the neighbor of u and the right neighbors of v do not intersect is if every vertex in my graph is in one of these two sets. Well, can every vertex be in one of these two sets? Well, one vertex cannot be in one of these two sets. Which one? U. U is not in one of these two sets because U is not a neighbor of itself, and it is not the right neighbor of a neighbor of V, because U is not the right neighbor of anyone, because U is the first vertex on the path. So therefore, not every vertex can be in one of these two things, but these two things together have size at least n, so they have to overlap. The intersection is non-empty, and by the argument above, we're done, because this means there is a green vertex followed by a red vertex, which gives us the cycle, which gives us either a longer path or the Hamiltonian cycle. Okay, so this is the proof of Dirac's theorem. If you have a proof like this, or a theorem like this, you always ask yourself, is this n over 2 best possible? Could I have asked for n minus 1 over 2, or n over 2 minus 1, or something like that? And the answer is yes, it is best possible, because I can draw you an example that's exact, that's a little bit smaller from the degrees, which is not Hamiltonian. So here is one example. So you take two complete graphs on half the vertices that share, or on the same number of vertices that share a vertex in the middle. So n is now 2s minus 1, and the minimum degree in this graph, what is it? It's s minus 1, which equals to n minus 1 over 2, which is exactly 1/2 smaller than the bound we have. And of course, this graph is non-Hamiltonian because it's not even 2 connected. Here's another example. Take a complete bipartite graph on 2s plus 1 vertices, s in one set and s plus 1 in the other set. Whenever I draw a cycle in here, no matter how I draw it, it's always going to have the same number of vertices in the left side and in the right side. So I cannot have a Hamiltonian cycle in here, because a Hamiltonian cycle would have every vertex exactly once, which would mean one more vertex in the right set than in the left set. I can't have that. And again, here my n is now 2s plus 1 in this case, and my delta here in this case is, the guys on the right side only see s vertices, which again is n minus 1 over 2. Again, just below our bound. So here are actually two different examples that show that Dirac's theorem is what we say sharp, meaning the bound is best possible. Right there, or here's the theorem, right? The n over 2, we cannot improve on the n over 2. And this is, if I talk about it, pretty interesting, because there's a lot of theorems in graph theory that have bounds like that. actually a part of graph theory that's called extremal graph theory, where you have a parameter of a graph that's like a threshold. If you're above that, the graph necessarily has a property. If you're below that, it might not. And then you're often asking for sharpness examples that are just below the threshold. And in most cases, there's exactly one of these sharpness examples. Here, in this case, it's interesting because there's two sharpness examples that have completely different reasons that they're non-Hamiltonian. The one has the reason that it's not connected enough to be Hamiltonian, because you have to be two connected. The other one has more of a parity reason, that it doesn't work out because of parity, even though it's very, very highly connected.